Hello everyone, welcome to the last Advent of Code stream. Today is the 12th of December and we'll be solving day 12 of Advent of Code. Now today is going to be a fun one. I'm not sure if you've read the problem yet, but it's going to be an interesting one. Hello Roger, nice to see you. Hello Ivan. Alright, so what does the problem statement say? By the way, actually let me move my face out of the way. This is what the home page now looks like. You have some nice animations of what I assume is Santa going around. It's pretty cool. Alright, so yeah, let's tackle day 12 because this is, like I said, this is going to be an interesting one. So what is it that we have to do today? Today we have to pack presents. So we are given our input is a bunch of two-dimensional shapes which are given by these pound signs in the 3x3 areas or regions. And after we're given some of these pieces, we are given some regions. So we have a 4x4 region and then some counts, and then a 12x5 region and then some counts, and then another 12x5 region and then some counts. And what these counts are is the number of each of these pieces you want to try and fit inside the region. So for example, let's look at the very first line of the regions. We have a 4x4 and we want to fit two of the second to last piece, which is what's done here in this diagram. Now this is, let me zoom in a bit more. This isn't great because this is letters, but essentially what they did here was you have a 4x4 grid. The region is 4x4 and they want you to figure out a way to fit two pieces that are this is going to be terrible. How can I draw this? Yes, let's fill this in. Alright, so there's a piece that looks like this and we want to fit two of them in this region, and you can do that because you're allowed to rotate pieces. So you can color this differently. How can I change the color of the... Can I not do it? Yes, I can. Alright. So they fit kind of like this. So there's a way, it is possible to fit two pieces of the U shape. This kind of looks like a U. You can fit two of these inside this region. How you say Christmas tree logic? I don't get what you mean, Nick. Yeah. So this is a way to solve the first puzzle, the 4x4 grid with two pieces shaped like a U, and then you have larger inputs. For example, this 12x5 grid, or in this 12x5 grid you want to fit a piece, one of the first pieces, and then one of the third, and then two of the second to last, and two of the last. And it's possible to do it. For example, the sample input shows you the problem statement shows you a possible arrangement where the letters mean different pieces. And then for the third one, you have another 12x5 region, but you want to fit one extra piece or shaped like a U. And as it turns out, there's no way for that to happen. It's impossible to do that. And so what you have to do is go through your puzzle input and count, given the pieces you'll be presented with, go through all of the different packing problems and figure out how many of them are solvable. So you just need to check if they're solvable or not, and if they are, you count them up, and then in the end you need to say how many there are. So for me that's going to be 593. So let's see how we can do this. Oh, and by the way, I forgot. you're given the pieces. Where are they? You're given some pieces, but they can also be rotated and flipped. So you have to account for that. All of the rotations and flips of the pieces are also relevant because you need to account. Actually, that's what we did here. The two U's here, they are rotated. All right, so how do we do this? Let's see, let me go ahead and go into the correct folder. Right, make dir day 12. Let's cd into that. By the way, did any of you folks solve this problem? Or are you trying to figure out how to do it as well? Right, so our solution goes here. Now I I also need my input. Where is it? Still trying. Yeah, I'll tell you what, this was not... By the end of this stream, you'll see that this puzzle was more intimidating than it was hard. But it's, I'll give you that, it's very intimidating, because this is called the packing problem in computer science and maths. And it's about figuring out the best way of fitting objects in a space. And it's not it's not an easy problem. And the best solution is essentially brute force. So there's no efficient, there's no super clever algorithm you can do here. You just have to try every single combination, and yeah. All right, so now let's start by parsing the input. So what I'm thinking is I'll represent the grid as a set with all of the points that are still free. So I have the pieces here. I'm going to represent the grid as a set of these points. So in the beginning, every single point is free, so the set contains all points in the grid, and as pieces get placed, the positions that are now occupied are removed from the set. And so when I try to place, when I want to check if I can place another piece, what I'll do is I'll have the coordinates of the piece by default. So if let me go here, I'm going to need this one later. If I look at this piece, let's do this in black. This piece is also in a grid, in a 3x3 grid. So what I'll do is I'll take care of I'll take note of the coordinates of each. What? Oh, because it's flipped. Interesting. Okay. I'll take note of the coordinates of each block. Let's call them blocks. And, sorry, give me a second. Just bear with me. I'm almost done. This is a 2, 2, 1, 2, and a 0, 2. So I will keep track of, for each piece, I will keep track of the coordinates of their blocks. And why are spheres mostly mentioned in the packing problem? Because this is, so the packing problem is like a generic name. Is a generic name for the type of problem where you have 2D shapes to try to fit into an area. And the problem that's mentioned here with the spheres is just a classical like variant of the problem where you want to find, and this is so interesting. Like, given an infinite plane, how well can you cover it with spheres? Because the thing is, obviously, like, spheres will never fit if they all have, or circles, if they all have the same size, you will always have gaps, right? Because, I mean, you can put two squares side by side and there's no gaps. between them. They just fit. So if you're trying to put lots of squares on a plane, you wouldn't do something like this, because now, like, you can't fit a square inside. So this is stupid. If you have squares, what you do is you put them just side by side. But this works with squares. Now with circles, this doesn't work. So what's the best way? If I have this white region here, this empty region, if I can only have copies of this circle, how well can I fill the screen? Because it's obvious that there's always going to be empty spots. So this is just so people think about the circles or spheres in 3 dimensions a lot, because it's a common version of the problem that's clearly very interesting. So how do you optimize this? Is this placement the best you can do? The one I'm doing? Yeah, so that's why they mention circles. Does that make sense? I hope it does. Alright, so for us, what we're doing here, thankfully we don't have to work with circles. What we're doing is keeping track of all empty positions as a set of those positions. And now, when we want to try to fit a shape, what we'll do is we'll check in turn, we'll go through the empty positions, which are all of these. We go through the empty ones in turn, and we take note, we check their, I don't want to fill it. Alright, so we check their coordinates, and then we take that coordinate, which in this case is going to be 3, 0. We take that coordinate and we add it, to the original coordinates. So, for example, the 3, 0 is the first empty position we're checking. So the top left corner becomes 3, 0 as well, because it's 3, 0 plus 0, 0. Then you're going to do 3, 0 plus 1, 0. So that ends up being 4, 0. And you keep going. So you do that for all of the pieces. And as you do that, or when you're done, you check if these positions are available in the grid. Because this is a set and this is a set, you just check if the piece fits inside the grid. And if it fits, you try to put it there, at least temporarily. And if it doesn't fit, you skip. And in this instance, you see that it does not fit because 4, 0 is already outside of the grid. So this fails. And when something fails, you do backtracking, you go back. So this doesn't work, you undo the plus, and you look for the, what am I doing? You look for the next available position, which is in this case 1, 1. Alright, and now what you do is you take the 1, 1 and you try to add it to your shape. So the 1, 1 plus the 0, 0 becomes 1, 1. And the 1, 1 plus the 1, 0 becomes 2, 1. And you keep going. And in this case, you see that after you're done adding 1, 1 to all coordinates, this would fit inside the grid. And so you try to make the placement. So you would move it here. And now for this specific case, you're done, so you stop. But if you had a larger grid, now you would keep going. You would try to... So if you had a larger grid, now you'd pick this position or this position and try to fit one of the other pieces here. And if it didn't work, you would go to this position and try to fit another piece here. And you just keep going. And in the end, if you couldn't solve the whole problem, you're going to do the backtracking, which means you figure out, okay, if this didn't work out, maybe I made a mistake along the way. For example, maybe in the beginning you tried... Can I please select the other one? Maybe in the beginning you tried placing this U in this position, and when you get to the end it doesn't work out. And so what you'll do is you'll go back in time, undo some of your placements and try something else. So if this fails, maybe you next try to do this, even though for us it looks worse, right? And then you can try to put it here, and if it doesn't work, then you can try to put it here. Alright, and that is likely to be a good idea. So this is the general idea of the algorithm. You can't be... Now you can also include some small optimizations, but you can't do a lot better. Do you have any questions about this so far? When do you flip? Yeah, also through backtracking. So one way to do it is, since we're going to spend a lot of time trying to place shapes, might as well just spend some memory in the beginning to grab a piece and figure out all of its flips and rotations, and treat them as separate pieces. So you build all of these. So there are essentially different things you can try to place. For this piece, there's 4 different versions, because flipping is the same as rotating. For other pieces, that's not the case. Flipping might be different from rotating. Yeah? Alright, I've been talking for way too long, let's write some code. By the way, I started solving before the stream. I set my code to run to attempt part 1, and just for the sample input, we're talking about the sample input. Oh no, I can't believe. No, you gotta be kidding me. My shell history doesn't... Oh no. I can't see how long it took to run. No, I'll try to do it again. Because I have, as per usual, I have some code already that solves it. Let's see what was going on. Let's remove these prints. Let's do this. Okay. So I'm trying to solve part 2. Sorry, not part 2. I'm trying to solve the sample input, and it's now working on the third example. Let's see how long it takes to run, because it takes a while. So let's close this, which is spoilers, and now let's work on this. All right, let's parse some input, because for this one it gives you have to work hard for your input to grab the information you need. So how do we do this? Let's see the pieces and the problems as a string. You're going to read the whole thing and split them into lines. No, wait, you're going to read the whole thing and then split in 2 consecutive new lines, because the input has these new lines separating the pieces and also the new line separating all of the problems. So you read the whole thing and then you split in those blocks. And now the problems, they're all consecutive, so you can grab everything else as pieces. Now these pieces are actually blocks. They're not pieces yet, because you get blocks like this that you need to parse. Alright. Now let's create a bunch of pieces. And now, because this problem was kind of complex. No, I don't need it. I was thinking if I was going to add type hints to the code for this live stream, but let's not do that. Alright, so let's create a list of pieces. And now we're going to go through each block and we're going to parse the pieces. And I want a piece to be a frozen set. And I want a frozen set instead of a set because I want to cache some stuff later on. And sets cannot be used in a cache because they're not hashable, but frozen sets are. So my piece is a frozen set that contains what? The positions x, y, where y comes from each line of the block. Now, a block is still a bunch of lines, so I need to split them. And I also need to skip the line with the index. And x comes from going through each line. But I only want to keep the positions where the character is a pound sign, because the dots, these are supposed to be empty. So I just keep the pound signs. So this gives me a piece. Now, for each piece, I also need to grab their rotations and their flips. So let's do that. Thankfully, I didn't, just for the sake of my own sanity, I didn't solve this problem in its full generality. I looked at the input and I saw, okay, all of my pieces are 3x3, or they fit inside the 3x3 region. So there's a couple of places where I use that information, namely the code here that's going to rotate the pieces. So I'm writing a dictionary that rotates all pieces in a 3x3 area. Now we're talking about the indices, not the actual blocks. For example, if I look at 0, 0, if I rotate it clockwise 90 degrees, where does 0, 0 end up? Well, it ends up at 2, 0. So in this dictionary, I map 0, 0 to 2, 0. And where does 1, 0 end up if you rotate it 90 degrees? It ends up at 2, 1. So 1, 0 gets mapped to 2, 1. So 1, 0 gets mapped to 2, 1. And we do this for all 9 positions. 0, 1. It's going to be 1, 0. And finally, the final 3. You could write code that does this for you. Wait, I made a mistake. 2, 1. This should have been a 0, 0, 0, 2. You could write code that computes this for you, but the time it took me to write this by hand beats the time it would take me to write the code that does it correctly. So I just went with the dictionary. And now we write a function rotate that takes a piece and returns the rotated piece. How does this work? You just return the frozen set with a rotation of each piece or of each block or each cell, whatever you want to call it, for each cell inside the piece. So this rotates once. Now what you want to do is grab all rotations of a piece. So given a piece, grab all 4 rotations. But some rotations might be the same, so what you'll do is return a set of those rotations so that you only keep the unique ones. So you're going to rotate your piece. What am I doing here? Right, okay, so to make it easier, you can say how many times you want to rotate. If n is 0, you don't need to rotate. Otherwise, you're going to rotate the piece again. This is a recursive function. Does it have to be recursive? It doesn't, sorry, my bad. I just like recursion way too much. So for... wait, I'm confused. This is the process that rotates. So what I'll do is for in range of n, piece equals this, and then you return the piece. All right, my bad. Sometimes recursion just pops into my head. So this will rotate the piece n times. by successively rotating by 90 degrees. And now what you'll do is rotate the piece n for n in range 4, which will rotate 0 times, 1, 2, and 3. And you put that inside the set so that you only grab unique rotations. And now there's also flip horizontal to flip a piece along a horizontal axis. Flip a piece along the horizontal axis y equals 1. And thankfully this is easier to write in code, so it's just the x coordinate stays the same and the y coordinate you flip it around. And for flip vertical it's a similar thing. Now take a minute to look at flip horizontal and flip vertical and let me know if they make sense to you. My bad. Yeah, I usually mute my microphone while I'm drinking water and I got too carried away. So for the sample input, the 3 problems from the sample input, it took me 464 seconds to run. This is 8 minutes for the sample input. So this tells you something about the complexity of this problem. And most time is spent on the third problem that is impossible. Now, funnily enough, I can solve part 1 in less than 3 milliseconds. So there's something cheeky going on. But let's finish this. Let's finish this code. So flip horizontal and flip vertical look like this. And now, once we get a piece, we can compute all of its variations. So all of the variations of the piece are the set that you get by grabbing the rotations of the piece and union that with the rotations of the flip horizontal and union with the rotations of the flip vertical. Now, I hope the math authorities don't revoke my master's degree. There's superfluous work being done here. I'm pretty sure I am computing some stuff repeatedly because flipping horizontally and vertically is the same as a rotation. Something like that. But I'll be honest with you folks, I just thought I don't want to look this up and I don't want to draw it out. I'll just write the code. This runs once, it's fast enough, it's not going to be terrible. So this computes all variations of my piece, and now I can append it. So I can save it for later. Now, one thing you can do that's quite neat is, for variation in variations, you can print the piece. So we can write a small function, print piece, that prints it. For y in range 3, for x in range 3, you print a character if this position is in the piece, otherwise you print an empty space. And now we can run our code. Actually, we need to call it because we're not parsing anything yet. So if name equals main, we parse the input. Now we go to the terminal and we run this. Actually, we need an empty line, otherwise we can't see the pieces. Alright, so if we grab the U shape, you can see it being rotated here. If we grab this piece, you can see it's being rotated and flipped and whatnot. So these are all of the variations. All right, so we're making progress. Any questions so far? Because parsing is a bit cumbersome, but well, to be honest, we're almost done with parsing. Or, yeah, if you folks have any questions later, you can always ask later. So we'll leave this here. Now what do we need to do? We need to parse the problems. So you might have seen in the other screen, because a problem is defined by, where is it? By the size of a region, and then the number of times each piece must be used. These are counts, so I'm going to use a counter to represent these, and this is just going to be a tuple with the width and the height. So let's go ahead and from collections import counter. That's going to be helpful. And now we're going to parse the problems. So for problem line in problem stir.split, because this is still a block with all of the problems, we're going to grab the dimensions and the counts, or the string with the counts, by grabbing the line and splitting on the colon. So we're splitting here to grab the counts on one side and the dimensions on the other. Now the width and the height, you grab those by splitting the dimensions on the x and turning those into integers. And the counts, you get them by enumerating the... Actually, I think this works. I didn't do this originally, but I think this works. So this is a string, you split to get all of the numbers, you turn that into a map, you map the integers, you map the built-in int to turn that into a sequence of integers, and when you enumerate, you get an iterable of pairs, index with count, index count, and the counter... no, it's not going to read it properly, I think. So let's do count stir uv run python. Count stir is equal to, for example, this one. Wait, what? Right, because it needs to be a string. So count stir is this string. Now from collection we import the counter, and then we test the line of code I wrote. Yeah, it doesn't work, because I was thinking that the reason I try this is because the dict, the built-in dict, will do this correctly. But when the counter gets an iterable, it tries to count those elements. So I could pass the dict to the counter, and that would work, I guess. Yeah. Alright, so this doesn't work directly, but if I do this, it works. But at this point, what do you think, folks? Is this line of code, is this production code, or am I going crazy? Is this production grade code, or should I split it? Should I write a for loop for this? Let's, I don't know. Everyone, you folks decide. Ship to prod, Anja says. All right, so let's do. This has been approved. All right. So this is a problem. We want to collect all problems in a list, and then we append with height counter. Marvelous. Okay, let me take a breather. I'm getting tired. What happens now? Now we do brute force. I think this is the time. Let's see. We have a piece, we have the variations, we even pretty printed the pieces, we have the problems. Exactly. So now we do brute force. So the overall look of our solution is going to be, or solvable equals 0. Actually, we're still inside parsing input, so let me return the inputs. So we return the pieces and the problems. Great. So pieces, problems equals that, and now we want to print part 1 of pieces and problems. Alright, oops, my bad, I didn't mean to jump there. So what do we do now? For part 1, we take some pieces and some problems. And my favorite way of solving a problem is offloading the work to a function I haven't written yet. So I'll say that the number of solvable problems is 0 in the beginning, obviously. And now we go through each problem and we call a function that tries to place the pieces on a grid with these dimensions and with these counter requirements. And there you go. Part 1 is solved. So now we just have to write the function place. So let me think. Do I need anything else? Nope, I don't. All right, so let's write this function that goes here. All right, as I said, I want to think of the region as a set with all of its valid positions. So that's going to be xy for actually just set of product of the range. So the x's come from the width and the y's come from the height. And I need to import product. So this is the Cartesian product. It's a very convenient way of getting all of the x's from width and all of the y's from height. So this is my region. And now I offload my problem once again to a helper function. So I'll return the place of the region and the counter. So this underscore place is an auxiliary function that's going to solve the problem based on the region set and the given counter. So the pieces, those are always fixed. It's always the same pieces, so I don't need to pass them in here because I'm going to define this underscore place in here. So region counter. Now, how do I know if the problem is solved? If I need to place a total of 0 pieces. If I get to this point, then this is true. It's solved. So this is a function that checks whether a certain placement is possible. So it must return a boolean. And in the end, if everything went wrong, I return false. So this is the template for my underscore place. Now I just need to fill in the gaps. So what do? I just test every single position. So for y in for y in range of the height, for x in range of the width, first things first, if this is not free, let's just skip it. If the xy is not in the region, we skip it. Okay, there's no way, if this is occupied, we can't use this. Now we try every single piece and every single variation of that piece. So for piece index and count in the counter, we check, do we still need this piece at all? Because some pieces eventually reach 0, and if we don't need it, we skip it. So if not C, we skip this piece. All right. Otherwise, I hope you're still with me. Otherwise, we have a bunch of variants to try. So for piece variant in pieces of piece index, because pieces is a list of sets of variants, this is the piece index. So now I grab the variants. And now I try to place this piece in position XY. So now comes the placement. And when I mentioned the placement, what I wanted to do, let me just check the time. We still have time. It's gonna work. It's gonna work, folks, don't worry. I was talking about adding the offset. Remember, if I want to try and place this piece in, I don't know, this cell right here, what I'll do is I'll look at the coordinates of this cell, the XY coordinates. I will add them to the base coordinates of my piece, because what I saved were the base coordinates on 0, 0, 0, 1, 0, 2, etc. And then I check if it fits inside the region. And in this case, it will, right? So I need this function that adds a position. And this adding is actually a translation. It's the geometrical term. So the function is called translate. It takes a piece and an offset. I break the offset up into the x and the y, so the small change in x and the change in y. And now I return the frozen set, x plus dx, y plus dy. It's actually amazing the number of times I wrote this expression over the past 12 days. X plus dx, y plus dy. For x, y in piece. And now because I'm going to be doing this a lot, and I really don't care about memory, I'll just cache this. I mean, I care about memory, but time is going to be more important here. So I can spend this memory. So I'll cache all of the translations. So all of the translations I do, they get cached for later because, yeah. Actually, to be fair, in the end, it would be interesting to check how useful the cache was. I think it's going to be useful. All right, finally, so we have a piece variant. We translate. So the piece is actually the translation of the piece variant according to this, to the place we're trying to put it in. And now we check if it fits. So if the piece, what's the way to write this? So if piece less than or equal to region, then the piece is fully contained inside the region and it fits. So let's do the following. If not, so if it's not contained, we skip. All right, if it is contained, the new region is the current region minus the places or the spots occupied by this piece. The counts have to go down by 1. So the counter of this piece needs to go down by 1. And we need to call this function recursively with the new region and this counter. Now, usually I have the urge to say return something, but I don't want to return immediately. If the recursive call ends up returning true, then of course I want to return the true, but if this returns false, I want to try the next variant and then the next piece and then a different position. Now, there's a good suggestion in the chat. Maybe it's possible to skip a problem if the length of the pieces times their amount. Yeah, exactly. So you can add some heuristics to make this better. That's one of them. We're going to add them really soon. Yeah. We're going to add that. Thanks for the note, Ivan. Yeah. All right. So we don't want to return immediately. We want to check. Can I place the remaining pieces in the remaining region? And if I can, then I return true immediately. There's no point in trying something else. But if not, then I'll try something else. If not, I want to reset the piece index. Now, actually, there's a better place for this, which is here. So these are all of the variants. We're trying always the same piece here, so we can decrement the counter here and increment when we leave the loop. So this is to avoid creating copies of the counter. So we actually modify the counter in place, but then you need to be careful to reset it if you see that this piece doesn't work. All right, so this works theoretically. I mean, actually, does it? I don't know, my code usually has bugs. Let me try this on the sample input because the first two problems should be solvable in a reasonable amount of time, even with my not optimized code, also known as unoptimized. Sample.txt. Sample.txt. Let's run this. Not enough values to unpack. Great. We're starting out just fine. Problem line 74. Problem stir.split lines, my bad. Alright, so it's running. I have no visual indication of whether we're on the first, second, or third problem. So let me fix that really quickly. So we're going to print the problem. Width, height, counter. and then we're going to print the results. Alright, so the first one is solvable. It prints true immediately because it's just the 2U's. It's quick at finding that. The second one should eventually print true, and the third one as well. Now we have a couple of heuristics that we can use to make this code faster. And they're not particularly clever. They're fairly simple heuristics. Let's take a quick look at the grid over here. Yeah, let's take a look at this grid, and let me extend the grid a bit further because it's 12 by 5. So that's 1, 2, 3, 4, 5, 6, 7, 8. So it keeps going. 9, 10, 11, 12. So some of our problems have a grid this big. Actually, one more row, but let's ignore the row for now. What I'm currently doing, suppose that I already placed these two pieces, it doesn't matter. What I'm currently doing is going through each available position and trying to fit something there. Now the thing is, each piece by themselves occupy only a 3 by 3 region. So I know that after trying to put something in the first 3 columns, like, I don't care about trying something else. Or rather, if I flip this the other way around, I know that for the packing to be possible, I need to put something in the first 3 rows. Because it makes no sense to leave them empty. So instead of going through the full grid, I can keep track of what's the last row that is at least partially occupied and guarantee that I don't go any further than plus 3 rows on that. Actually, this is column, sorry. And we can do a similar thing for the rows, because for large grids, that's going to save a lot of time. Do you understand what I'm saying for this small optimization? Alright, the second one was solved. The third one is going to take a long time. It took 8 minutes with the optimized code, so it's going to take much longer with this one. I'm going to interrupt it. So let's implement this small optimization. What we're going to do, let me close that, is keep track of the last row used and the last column used, which is at least partially occupied. And in the beginning, I haven't used any rows or columns yet, so let's do -1, -1. And now when I call the function recursively, I might need to update this, because the piece I just placed might extend to the right of the last column that had been used, or under the last row that had been used. So what I'll do is I'll compute the bottommost position of the new piece in piece, and I'll compute the rightmost position of the new piece. And then I say that the last, which one is it first? Last row used. So the last row used is the maximum of what I already have used, or the bottom position of this piece. And for the last column, it's a similar thing, but with last column used and the rightmost position. And now, if we run the code, it still works. It's just slightly faster. It still takes a while, but it's faster. I thought this was going to take only a couple of seconds, as opposed to the couple of minutes that it took before. But apparently it's not that fast yet. Okay, but now we can work on the... Okay, so it did finish. It took less than a minute to solve the second sample, which is already faster than what it was before. And now we can implement the heuristics that Ivan was mentioning, to skip some problems as obviously impossible, or to solve some problems as obviously possible. For example, let me open my diagram really quickly. Suppose I have... This is going to be a pain to oops, I need to draw a grid. 5, 6, 7. 1, 2, 3, 4, 5. Bear with me, just one more. 6. All right. Now it's a bit longer than it needed to be. Let's ignore whatever's on the right. I have a 6 by 6 grid. Quick question for everyone in the chat. If I have 4 pieces to place in total, is this a solvable problem or not? Or do I have to tell you what pieces I'm thinking of, if there's only 4 of them? Come on, everyone. If there's only... Right. Okay, so there's one thing missing, which is... Don't forget that every single piece fits in a 3x3 region. So what you can do in this case is... You can split your grid in 4 3x3 regions, and you don't even have to be clever. You can put one piece here, another here, another here, and another here. It doesn't matter how you do it. It doesn't matter which pieces there are. They just fit. Yeah? So that's one. So some problems hopefully will be so easy to solve that you can just do this and you don't have to worry. And some other problems, which is what Ivan was saying, let me tell you this. A 6x6 grid has 36 squares. And the piece, this U, has a total of 1, 2, 3, 4, 5, 6, 7 squares. Is there any way on Earth you could fit 6 of these pieces, 6 U's in here, in these 36 squares? There's no way in hell, because 6 pieces, each occupying 7 squares, would require a total of 42 squares, but you only have 36 available. So not even if you could cut these up, even if you cut them up, there's no way in hell they fit. So this is, I think, what Ivan was suggesting. You check something like this. Now, obviously, this doesn't solve all problems, because, for example, 5, if you think of 5 U's, if you think of 5 pieces of the shape U, you get 35 squares, which fits under the 36. Now, can you really flip and rotate the piece U so that it fits 5 times into this grid? I hardly believe you can. I don't think you can. So you can't use this heuristic to solve all of your problems, but it helps. Now, the first assumption is valid because the side mean size is 3, right? What do you mean by the side mean size? I took a look and I saw that every single piece fits in a 3x3. If that's what you're talking about, then yes. Alright, let's bake these heuristics into the code. If we had a piece with 2x2, then you could try to have an heuristic that's even more aggressive. But because every piece fits into a 3x3, you can just try splitting the region in sections of 3x3, yeah. So it is dependent, the split we're doing here for this heuristic is dependent on the dimensions of the pieces you get in the beginning. You're right. But ours all fit nicely in a 3x3. Okay, let's work with this. Let's go to the code. By the way, is it still running? Yes, it's still running, still trying to solve the third instance of the sample. Great, so now we have a bunch of problems. We want to avoid calling this function whenever possible. So we'll do the following. We'll count also the problems that are definitely impossible and the problems that are obvious. And fingers crossed, we get to cut some work with these. So which ones are definitely obvious? The ones where each piece has a 3x3 space all for itself. So the total number of pieces is given by the total of the counter. So this is however many pieces you need to place in total. And the number of 3x3 subgrids is given by the width divided by 3 times the height divided by 3. So if the number of pieces is smaller than or equal the number of 3x3 subgrids, this problem is obviously solvable. And you can move on to the next one. All right. Now, is this problem impossible even if you were to cut pieces into blocks or into squares? How do you do that? Well, you first need to, or how do you check that? First, you need to count the total number of cells that your problem wants you to occupy. So that's going to be the sum of the number of pieces times the piece area. Now, what's the piece area? It's the length of its set. Now, the thing is, I'm thinking, so pieces is a list of sets. Pieces is a list of sets. How do I grab one variant? Okay, so what I'm trying to think is, how do I get the area of a piece? But it's easier to compute it in the beginning than when I have a set, because it's not easy to take a look at a random element from a set. So let me think for a second. So we have the variations, pieces append. We'll also append the piece area here, which is going to be the length of the piece. So now pieces is a list with the length of the piece, or rather the area, and then all of its variations. So we need to update the code here, because we only want to pass the variants. So this is the pieces set. For area, pieces set in pieces. All right, and in here we can grab the tuple and the area of the piece for each index and number in, or rather than number, let's call this quantity. I find it slightly more descriptive, for each index and quantity in the items of my counter. All right, and now if the total area needed is already greater than the area you have available, let's print this is obvious, then this becomes impossible, or this is impossible. And you can say that this one is impossible, and you can move on to the next one. All right. Now, funnily enough, and it's still going for the sample. Now, these new heuristics, assuming I didn't break the code, of course I did break the code. Object of type int has no length, right? Because I already gave it the area. I don't need to compute the length. This is already the area. So obviously, for the sample, this does nothing because all of these problems, none of them are obvious. But what we can see is that for the full input, this kind of helps. And in the end, where's part 1? In the end, let's print all of them. So we print the obvious, we print the impossible, and we print the solvable. And now, sorry, did I save it? For the input. And now we run this. And there you go. Part 1 is solved because 593 problems are obviously solvable. The other 407 are obviously impossible. And you actually didn't have to worry about any of them. So I spent the full last hour writing code for nothing. Can I get a like for this? You have to, you have the more, if you're watching, you have the moral obligation of subscribing to my channel after I wrote all of this code for you, to show you how you could solve this in theory when in practice you didn't need any of it. And everyone in the chat is speechless. No one said anything. Thank you for the thumbs up. Math authorities made a payback. Yeah, there you go. Day 12 in a nutshell. I think the code that actually does the solving is kind of neat, and it's not. Oh, I forgot. Oh, come on, folks. That's why it didn't finish in the 8 minutes it should. So I implemented the last row used and the last column used, and that's supposed to go in here, so we avoid going through the full grid. So for the height, you do last row used plus 3, because you might need to use one of the new ones, but you don't have to go too far down. And for the width is the same thing, but with the columns. I mean, it doesn't help a lot because the sample is still going to take 8 minutes, and the input, if I didn't have the heuristics, it would take ages. But it helps a little bit. Alright, it helps a little bit. Now, yeah, of course, for the input it makes no difference. Okay, everyone, any questions? This should be, we've been here for 1 hour and 4 minutes already. Plus the obvious, because we want to compute the ones that are solvable. Yes, 593. So this was part 1. And when you check, part 2 was free. Usually on the last day of Advent of Code, you only have one problem. So for part 2, you don't have to do anything, really. Alright, everyone. I hope you had fun. I cried a bit when I was solving this, but to be honest, I did have fun writing all of this code. Both times I did it, when I was doing it for myself and for the stream. I hope you learned something through or during these 12 days of Advent of Code. If you want at any point, feel free to reach out to me on social media, or you can drop me an email. Where's my contact me? So feel free to drop me an email at any time. Maybe I should move my face out of the way. So rodrigo@mathspp.com. Let's paste this in the chat. I'll be around. I don't think I'll be streaming tomorrow because tomorrow there's no day 13 of Advent of Code. Although I might start streaming regularly about something related to Python. We'll see if I have a good idea and if people show interest. But yeah, that's it. Day 12 is wrapped. And unless you have any questions, I think we can call it a day. Thank you, Roger and Ivan and Anje, for showing up today and for interacting. And that's it. Thank you, bye. Thank you, folks, and bye. Yeah, and Merry Christmas. Bye, everyone.